Alrighty, good morning and thank you for coming out to attend our capstone design presentation of fluorescence, a sensor for engine oil replacement using fluorescence detection and molecularly imprinted polymers. Myself is Brandon, this is Alan and Michael, and out attending our booth right now is Danny and Tyler. So engine oil is one of the most essential maintenance items of a vehicle. Its function is to provide lubricant as well as wear and corrosion resistance to all moving parts of the engine. Simultaneously, the engine oil is going to clean and filter out large debris that can form up in the engine over use. And due to incomplete combustion within the engine, there's going to be a degradation of oil over time. So eventually, about 5,000 to 10,000 kilometers or so, you're going to have to undergo an oil change. Now, in almost all modern vehicles these days, there's oil life monitors. Now, these oil life monitors take into account a number of different variables, such as the total kilometers since the last reset, engine revolutions, drive cycles, engine temperature, throw it all into an algorithm and output the oil life percentage. Now, the downside to this is it's just a calculation. It's not a direct measurement. So there's many inaccuracies that could be present globally, such as different climates, as well as different driving habits, the type of oil, the age of the vehicle. These can all increase the amount of inaccuracies that are seen. So what's this mean? Well, if you're using overused oil that says, and your oil life monitor is saying that it's okay to function, you could be damaging your engine. Or on the other hand, if it's underused oil and you go and perform an oil change, then you're gonna drive up the cost of your maintenance fees for a vehicle, which any owner is not going to really appreciate. So the industry standard, we believe, should be a direct measurement of the oil and not just a simple calculation base. So, found by Grimmer and his colleagues, as engine oil degrades over time, there's an increase in the concentration of polycyclic aromatic hydrocarbons. Now, these hydrocarbons, since they are aromatic, they do readily fluoresce. That we plan to detect the fluorescence of these aromatic hydrocarbons and change it into a concentration. So that over time, as the concentration of these PAHs increase, the fluorescence intensity is going to increase, and we'll have a critical point at which the user is notified to change their engine oil. Now, each aromatic compound does have a unique excitation wavelength and emission spectra, which we're going to take to our advantage in order to pick a compound that's best suited for our needs. So seen here in the table and highlighted is parylene. Now, all of these different polycyclic aromatic hydrocarbons are found in oil at the concentrations over to the right. So the concentrations listed there, the mins and max, are for engine oils that have been driven a total of 1,000 to 6,000 kilometers. So for parylene, for example, it has a concentration value of 1 to 10 milligrams per kilogram, with even going up to 50 milligrams per kilogram if driven about 10,000 kilometers or so. So parylene, as a molecule, has an excitation wavelength of 410 nanometers, with an expected emission spectra between 435 and 465. As well, parylene has a quantum yield of about 94%. So with both these two characteristics, we've used this to pick parylene as our target molecule, just because a lot of the other compounds that was listed in that table have excitation wavelengths in the UV range, and we really didn't want to make that complexity into our initial prototype. So overall, what we plan to do is develop a system that uses fluorescence spectroscopy to determine the point at which the engine oil should be replaced. When the concentration that's calculated from the fluorescence intensity reaches a critical value, the user will be notified for that change. What our requirements are for an actual product would be to accurately measure the molecule within 1 to 50 milligrams per kilogram, to maintain that accuracy over the engine temperature environments of 80 to 110 degrees Celsius, a response time in a single drive cycle, as well as stability during the motion. But a minimum requirement for ourselves to deem our project a success was to detect the difference between a new oil signal and a used oil signal. So the secondary and tertiary customer requirements are more so geared for a final vehicle installed prototype. That would be the high accuracy over the lifetime, low cost, compact size for ease of installation and removal, as well as build in other sensors into it, such as an RGB sensor, which we'll get into, and create a mobile app interface to make it more user-friendly. The functional specifications, though, are to make sure that our initial prototype is going to function as we want it to. That would be to measure, again, the range of 1 to 50 milligrams per kilogram, to excite at 410 nanometers, and a diode that's fine-tuned to collect between 435 and 500 nanometers, run off a 3.3 volt power supply, a response time less than 5 minutes, and keep it as a compact size, about 10 by 10 by 8. So to talk about our actual prototype now is going to be Allan.
All right, thanks, Brian. So I'm going to talk to you about the prototype that we've been developing for the past 8 months. It's pictured here. It's also on display at our booth. So to start the design process, we started with the selection of a microcontroller board just to handle all of the logic. We had a huge array of things to choose from just because of the huge developments in the past few years. We have Arduinos and Raspberry Pis. We ended up going with the BeagleBone just because it's really versatile. It has Linux built into it, so prototyping is just really fast, it's really easy, and it runs Python. So instead of having to code an embedded system, we could just do rapid iterations in Python. We also found SPI, GPIO, IC², and other libraries that could be used and integrated really easily. When we came to selecting our optoelectronic components, Brandon talked about the specifications we needed based on our research with Parylene. We needed a LED that could excite 410 nanometers, and we needed a diode that could read 435. Most of the components we found obviously had really broad peaks. And without the use of a diffraction grating to separate out the wavelengths, we found it really easy just to use a filter to get the overlap really low so we could isolate our signal really well. Moving on, we used two really common DAC and ADC converters that we found. They're 12-bit, which is really high resolution, perfect for what we need. And they could also communicate via SPI to our BeagleBone, so that made that part of it very easy. For the photodiode, we connected it in photovoltaic mode because we needed a really high accuracy as opposed to a fast response time. This made our signal really low, and we had to boost it. I think we had a boost of around 250K through 3 op amps. Thanks, John Saad, for helping us with that. And once we had all the components in place, we had a breadboard, microcontroller board, and all the optical components, we designed a jig that could be used in the lab for really quick testing of all the samples that we made. And here's actually Michael to talk to you about that.
Thank you, Allan. So in order to validate our design prototype and ensure that it was working properly, we tested a series of samples in clean, brand new engine oil, which we spiked with increasing concentrations of Parylene. Parylene was dissolved in toluene and put into these samples at concentrations across the expected range of Parylene in the dirty oil, which, as we mentioned before, was between 1 and 50 milligrams per kilogram. So as you can see from the plot here, these are the signals we obtained from each of these samples. The trend observed for the data set was logarithmic. So as the signal continued to increase with increasing concentration, the differences in signal increase between changes in concentration got smaller and smaller as we approached our maximum concentration limit. This was somewhat expected because the effect of concentration quenching would likely begin to dominate as the concentration of Parylene increased. However, because the trend remained positive and didn't quite flatline, we can still calculate accurately the concentration of Parylene across the full range. At the maximum concentration we tested here, which is about 37 milligrams per kilogram, signal-to-noise ratio of about 105 was observed after we accounted for the baseline and the 5 millivolt peak-to-peak swing that we had as noise. A signal-to-noise ratio of about 20 was observed at the minimum concentration. Due to the logarithmic nature of the plot, we calculated 2 limits of detection based on the 2 linear portions of the curve. The first portion, which is in the low concentration range, up to about 10 milligrams per kilogram, we were able to calculate a limit of detection of about 150 micrograms per kilogram. And in the second portion of the curve, the flatter part, we calculated a limit of detection of about 1.1 milligrams per kilogram. So after meeting these requirements for our limit of detection in the clean, the next step was to test the device with used dirty oil. Oil gets dirty with soot and other contaminants as it ages, turning it black and therefore decreasing our overall signal intensity. Two potential solutions to this problem were considered, the first of which was reducing the optical path length over which our measurement was made. This has the effect of lowering the overall optical density of this oil, allowing more light to travel through it, and therefore increasing our signal. The effect of the path length for the cuvettes we were using was simulated by diluting the oils with a clear solvent, in this case we used toluene, to lower the optical density. So after we diluted them to the densities we wanted, we spiked them similar to the way we had spiked the previous samples. So as you can see from the data here, all the curves we had calculated were linear, and the slopes increase with increasing transparency of the oil. In samples 75 times more clear than the original oil, represented by the yellow line there, a path length, this would represent a path length of about 130 micrometers, and a signal-to-noise ratio of 85 was obtained at the maximum concentration. However, this path length isn't very practical to implement in an actual system. With only a 10 times increase in transparency, represented by the green curve, we were able to get a signal-to-noise ratio of about 7 and a limit of detection of 5 milligrams per kilogram. This would represent an optical path length of 1 millimeter. And while the data is obviously not ideal, it does show that it is possible to get a signal. So to improve our signal, we have three options, more or less. To decrease the amount of noise we have in the circuit, to boost our overall signal intensity, or to create a system that works with lower effective path lengths. And this leads us to our second potential solution. So if we were to use a molecularly imprinted polymer, or MIP, we believe we can overcome the problems described before by both lowering the path length and increasing the overall signal. The MIP is essentially a polyurethane material with the special property of having preferential binding sites specific to one's analyte of interest. How this is obtained is by introducing the analytes during the polymerization procedure so that the polymer essentially forms around the analytes because they can't be incorporated into the polymer chain. Once the analytes are removed, typically by using a heating step or a washing step, these sites are left behind at the polymer surface, and due to their preferential rebinding, the MIP can act as a sort of concentrator for, in this case, perylene. So if we were to place this polymer at the surface of our sample container, the effective signal can be increased because the light now only has to penetrate the thickness of the polymer film, which reduces the optical path length and increases our signal. We made a first pass at synthesizing this polymer following a procedure outlined by Dickert et al. In analytical and bioanalytical chemistry. So this involved a polyurethane reaction using a diisocyanate material and polyethylene glycol in a solution of pyridine. Perylene was added at a concentration of about 5% of the total mass of the solution. Despite the polymerization proceeding seemingly well, it was very difficult to spin coat a nice even film on our glass substrates, as you can see from the images there, because the solution had a very low viscosity. Unfortunately, due to some other unforeseen issues that we encountered while prototyping and assembling our circuit, further development of the polymer was put on hold. The only validation test we managed to complete was to essentially confirm that perylene was removed from the film, which we tested by exciting the glass substrates with our LED and observing no fluorescence. So now I'm going to pass it back to Brandon to go over some more analysis.
Thanks, Michael. Alrighty, so we made a device. We spiked it with perylene. We were able to fluoresce that perylene, and we were able to detect that signal that it gave off. We're done. We met our minimum requirement, but there was some other benchmarks that we tried to hit here too. We were able to detect perylene between 1 and 50 milligrams per kilogram as we wanted, with a response time of only 20 seconds and all at a low cost. The advantages over the oil life monitor I previously talked about is with a direct measurement, we're bypassing those inaccuracies that were going to be from the calculations. The sensor's not dependent on a technician resetting it. We're not going to have unwanted oil changes and a loss of money. And as well, we're going to have a less risk of damages to the engine because we are changing the oil at the proper time. Limitations with our current device right now, like Michael mentioned with the optical density issue, a couple different options there. We would have to form calibration curves of every single type and brand of oil since the critical parylene concentration would be different among each one of those. The current prototype that we have is slightly unstable when shifted and moved, so once put into a vehicle that gives us a bit of a limitation. And finally, at low concentrations of parylene, it's difficult to actually detect with our low signal to noise ratio. So all in all, at the end of the day, we have proven that this concept will work of a direct measurement over the calculation based, all at a pretty low cost of only about $412 is what we've put into the prototype right now. So will this go onto customer shelves as is? No, it won't, but maybe Allan's going to give some future improvements here to get it there for us.
All right, thanks. So I'm going to just go quickly through this section. As you can tell, $411 is quite outrageous for a sensor. So we've taken a few kind of considerations to reduce the price to around $50, which would be a common sensor that you'd find in a regular vehicle. One of those is to move to an embedded system. These could have built-in CAN. They reduce the overhead, and they're really commonly used in a lot of common engineering. We have designed a PCB. It's a two-layer PCB that could have been manufactured. It's currently designed to work as a shield for the beagle bone. This could be kind of arranged to fit our new geometry in the final design prototype. And we have a few other considerations other than what Michael currently talked about was the oil library. Various oils would have different curves that we'd have to calibrate the device for. We could have this on chip or maybe just preloaded into the firmware when the device is installed. And the enclosure design would have to resist the really harsh conditions of the engine bay. And of course, lifetime would also be an issue. We'd want to target around 100,000 kilometers, which is the average vehicle lifetime for one customer. So that being in mind, we'd like to thank all of our advisors and people that helped us with all of our questions, and Jen Coggin for letting us use her labs. So we'd like to hear your questions now. Thank you.
Great. Thank you very much. We have time for a couple of questions. In the interest of time, we can't really spend 4 or 5 minutes, but Chris.
Okay, so I'll try and keep this quick. So if I understand correctly, you've made measurements, calibration measurements that indicate that with a 1 millimeter path length, you can get a yes/no answer. It's old, replace it, or it's new enough. No, right?
Yes.
Okay, and then if I understand you correctly, to go further, to get something that's qualitative to say, you're 50% of the way through the lifetime of this oil, you need a method.
That would essentially enhance the signal we're able to achieve. Like you said, right now it's more of a yes/no. You can either say it's there or it's not.
Can you do it without the method? Can you go further? Get like 50%?
I have a comment on this. The oil in the engine would be very non-deterministic and a lot different from the cuvette environment.
Right.
It's sloshing around, there's gunk, there's metal particles. So the MIP is just one of the ways we try to mitigate the problems that would come from actually going to the engine bay environment.
One of the solutions we could do in the immediate future was to possibly use front-facing geometry so that we are measuring the basically the LED and photodiode are on the same side of the cuvette, and we would measure the fluorescent intensity from just the one surface. And that would probably require some better filtering and all of that. But that would be, I guess, something we could try in the immediate future.
Okay, thank you.
All right. I think we can take only one more question. So,
just an easy one. So, did you guys try I don't know if you had a car, did you try like a real?
Yeah, so luckily enough we had access to an auto shop where we're taking many different vehicle samples at many different kilometer ranges. What we found with ours, because of the signal to noise ratio, it was very difficult to determine, okay, is that a 2 millivolt range? Is that a 4 millivolt range? So say we took engine oil that was 3,000 kilometers used and engine oil that was 6,000 kilometers used. We could tell that it was used. Could we tell a difference between the two of them? Not quite. There are many other factors that come into it, like I mentioned, the types, the brands, and the age of the vehicles. So to answer your question on a scale and differentiate different oils, we're not quite there yet.
All right. Well, I think we have to move on. So let's thank the team once again for the great